page. This is a meeting with a lot of co-hosts with Electron device and 10 out 5 Affinity group, as well as the Central Texas Consultant Networks. So we have a Dallas, Denver, Fort Worth, Houston, Kansas City, Lone Star, Oklahoma City, St. Louis, Wichita, and Central Texas.
So my name's Luis Basto. I'm the chair of the Central Texas Consultants Network. We have been having joint meetings with the live members group for, I guess, the past 2.5 years, ever since COVID. So, and we actually started live meetings a couple of months ago, but this month, due to our speaker not wanting to expose us, so we changed it to all virtual. Anyway, the Consultants Network, we promote the development of members' careers through professional and social networking, including publicizing member skills and sharing potential professional opportunities, and supports the IEEE Central Texas section. Our web page is very ancient, but there is actually a tab in there that says members, and which obviously hasn't been updated for a while, but every now and then actually I added a new member who asked to be added. So if any of you interested can go look at that. You can request to be added there if you like to be in the Consultants Network. And IEEE, of course, is a very big organization worldwide. We have over 360,000 members in more than 160 countries, and have lots and lots of journals and magazines and professional transactions. And we hold about 1,300 annual conferences around the country and around the world. Okay, next, please.
So this is my group, the live member. That means we are all over 65, and with a number of years of membership equal or greater than 100. So this is our team. Tom is in Illinois, the rest are in Austin. And our goal for this year and also maybe next year, so we want speakers. We want people in the group to be speaker. And the topic, we like technology, we like 5G, 6G, IoT, AI, smart city. And also we want to look at the finance, hobby, travel, education. We want to hear your story and your contribution in the past. We like to add health and aging topic, as well as the history of engineering and science, any major event in the past. A little bit forecast in the next few months. Next month, we change it to 29th of September, the fourth Thursday, because the speaker, Mark Campbell, will be our town. He's actually speak from Colorado someplace. And he's going to talk about venture capital and tech startups. So he was a speaker in the Denver Computer Society earlier in the year. I was there and I found it very interesting. So I asked him to do the same thing for us. It's a very interesting story from the 50s, 60s, how Hewlett Packard and set up, and then you have Fairchild and all a bunch of other tech and Intel and the rest of history. So how the market started with venture capital. October, we have a mathematician, L. Rice, talk about a math topic, extreme value analysis. So physics and math are everything behind all the engineering. So I think that we find a math guy to talk about. He works in the aerospace industry. November, we plan to have a Wayne Coswell and talk about, he's a host for the healthtalk.com. It's an information page for the for people who want to take care of the elders. The topic is how to do senior living options. What kind of option? You want the aging in place, or find a nursing home, or find some active living options. So I want to talk about that. And also we're thinking about a member, live member appreciation lunch. Is to be determined, not decided yet, maybe end of the month or sometime before December. Tonight's topic, semiconductors golden years. So we call the 1970 to 2000 as the golden year, especially in Austin, and for the company, a few of us work for Motorola. So if you look at the history, we're kind of peaking out in the mid 90s. We're hiring people left and right. We bought number of fabs. We're adding trailers in our campus one a month. That kind of the local county law allows you to do that. You're adding trailer for temporary housing, which keep them there. Still, we are told to take them down. So we bought 2 fab, and we always ran the top 5. I think one year we're number 1. Then later on in the late 2000 or late 90s, we break up. We sold the on semiconductor that handle all the discrete, some of the less complicated product. Then our number drops, our revenue drops. But we were top 5 before, probably the whole decade. And Mike is a engineer. He joined Motorola in 1978. He worked in Houston as a field application engineers. And he moved to headquarters in Austin, or regional headquarters. Then he became the DSP marketing manager in 1989. Then later on, he moved in a different project. He became project managers and doing R&D project. And probably you read that in the intro of the farm. I'm not going to repeat that. Basically, we think 1970 to 2000 is a golden year for Motorola, and also maybe for the industry, because we build all the basic elements that enable all the system on chip, all the new thing that's going on now. So Mike, I'm going to answer myself, and you can start sharing yours.
All right, thank you, sir. Give me a second here to find the right thing to click on. I'm Mike Collins. I was born and raised in Tulsa, Oklahoma. Glad to see people from that area in Wichita. I have relatives in Wichita. I was always interested in electronics, and I started as an application engineer, which meant I supported everything semiconductors had. And in order to support this, there's no way I could remember any of this. So Motorola published these master selection guides that had everything that they made in every single chip. And this is from 1979, which is I started in 78. So that's pretty representative. I got one from 1986. I got one from 1997, so I got some pretty good sample points. There was also a price list. This is from, let's see, 1997. So if you want to know the price, 100-piece quantity of a 5.6-point Zener diode for 68,000, I can give you that. I also like the history of Motorola, and for some reason I bought this thing, which is a Motorola radio manual that shows the car radios, the home radios, and other products that Motorola had in the 1940s. I also bought the things you'll see later, some ads that Motorola came out with. And so I wanted to kind of represent Motorola well and just speak from facts and not just my memory. I also would like to, let me see how I get this into sharing again. Hang on. So I feel like I'm sharing more than just this window. I'm sharing the,
It's your girly pictures, Mike.
yeah. Oh, there we go. I think that's what I want. There we go. So I want to thank Kai for introducing me and bringing me here. And I joined Motorola Semiconductor in '78, worked there 30 years. I want this presentation to be interactive. I'll give you my presentation. It's my little viewing through a straw. And I know Tom Starn just spoke up. I work with Tom. Kai, I worked with Kai. Feel free to speak up. If you have worked for other companies or Motorola, just jump right in. But I'm really excited to be here today. And we're going to talk about galvan manufacturing, which is the early days of Motorola, and the Motorola Semiconductors, which is the birth of the semiconductors, the various product lines, some applications, and the split up. So let's go back to the 1920s. Radios. This is a circuit for an Atwater Kent radio. Notice they came in with an antenna, and they had a gain stage and a tuning filter and a gain stage and a tuning filter and a gain stage. There was no intermediate frequency. You had the three little knobs, you had to tweak all this stuff up, and then you finally get a little amplifier, but it still went to headphones. There weren't speakers back then. Also notice that it was powered off of batteries. So there was a thing called an A battery and a B battery. The A battery, these here, were about 2.5 inches in diameter and 6 inches tall, and they were 6 volts. The B batteries were 45 volts. And you had to have a couple of these in series in order to, get the voltage up for the grids. Most of these were screw top. Some had this little weird connector. And this little weird connector, you could push down and stick a wire in there, and that was kind of cool. So this is an age test. Can anyone tell me, I'll take 5 seconds, what's the name of this clip? Anybody know the name of this clip? Okay, I'll take that as a no. It's called a finesse stock clip. And this finesse stock clip was patented in February 26, 1907 by John Shade, and he assigned it to the Finesse Stock Electrical Company, which I think was someone's name. And that's how that happened. And the Finesse stock clip, I remember as a kid with electrical kits and stuff, they had that a lot. And so the aftermarket things where people would add to the phones, they would add amplifiers and speakers, and then they would also add something called a battery eliminator. And the battery eliminator plugged into the wall. Back in the 1920s, about 35% of the households had electricity, and batteries were consumable. And so they made these gadgets to plug in and replace the A and the B batteries. Of course, we know this today as a power supply. In 1928, Motorola started in Chicago as galvan manufacturing, and they built battery eliminators. And that's what I knew beginning at Motorola. But it wasn't until I dug deeper that I found out that the brothers Paul and Joseph Galvan bought the battery eliminator schematics and plans and the rights to manufacture from a bankrupt company called Stewart for $750. They started making battery eliminators, but then eventually radios started to integrate more. They started to add power supplies to their radio. They started to add amplifiers to their radio, and that started to kind of dry up the battery eliminator market. So galvan manufacturing needed something else. They needed more products. And it turns out that they learned there was this guy that he started to integrate a radio into a car. And this guy named was Bill Lear. I don't know if Bill Lear rings a bell, but Bill Lear created the Learjet. Bill Lear created the 8-track tape. Bill Lear was a Navy engineer. He learned other electronics after that from Stanford, and he got 120 patents. And so Bill Lear and his buddy were out one day with their girlfriends, and they went to the beach. And the girl said, "Hey, wouldn't it be cool if we could listen to the radio in the car?" So that challenged them, and they had to solve several problems. One was getting the radio in the car. They had a motor generator to generate things, so the electricity required. The spark plugs create a lot of noise. They had to have spark suppressors, and they designed this entire system. And the Galvin manufacturers learned about it, and they really licensed it from Bill Lear. So Galvin Manufacturing demonstrated a working model in 1930 at the Manufacturers Association Convention in Atlantic, New Jersey. They brought home enough orders to pay for building more. They hired other engineers and manufacturers. They had about $565 in working capital. But they sought more working capital, and so they went to a bank. And a banker said, "Hey, sounds good. You know, can I get one in my car?" So they installed a Motorola radio into the banker's car, and it turns out that the car caught on fire. So needless to say, they didn't get the loan that they needed for that. But there was enough orders to keep them going. And back then, the Ola name, Radiola, Victrola, that was a suffix that kind of was common. And so when they put a radio in a car with a Motorola was the name that was coined, and they went public in 1943, and they changed the name of Galvin Manufacturing to Motorola in 1947. So up here is a picture of the original 1930 car radio. In 1932, you can see that it cost about $50 for a standard, about $70 for a deluxe. They had these little cars that were demo vehicles, and in 1932, they could drive around and show people what they had. So anytime you want to jump in and ask a question, I'm open to that. That kind of got them going. In the 40s, things grew. They had more consumer products. They made televisions. A 7-inch television was $180. They were big into police and fire. Here's a desktop two-way radio for police, and here's the one in the car. You can see over here on the right is other televisions they had. The Motorola logo for radios and military. The World War II helped them out a lot. They created the walkie-talkie, which is all this is vacuum tube technology. They created radios, they created Victrolas, and then a guy named Dan Noble decided to pursue FM technology. So they actually had, this was a US soldier backpack from 1943 demonstrating FM technology, which made a clear signal and a better thing to transmit by. They decided that automotive was the way to go. They tried some other things. Being in Chicago, Chicago's cold. Motorola came out with a push button gasoline car heater. Just look at this thing. It starts in 33 seconds, even as 50 below. They had a push button heater to go to 50, 60, 70, 80 degrees. Constant heat, even when the car is off. And I actually bought the installation manual for this thing. And this solid line demarcates the passenger compartment where they had the heater. Outside of that is the car gas tank. This is the fuel line going to the automotive. And all you got is the motor. All you got to do is just tap off a little gasoline and bring it up to this little pump and pump gasoline into the passenger compartment and turn on this little furnace. And what could possibly go wrong? So I just thought that was kind of interesting divergence for Motorola galvan manufacturing. So all this time I've been talking about what does it have to do with semiconductors? And this has been leading up to that. And I'm sure you guys have a lot of comments or questions or things you want to contribute, but my little path along the way about semiconductors brought me to this. There were a lot of physicists over the last 100 years experimenting with different materials and their capability. And of course, you know, the crystal radio cat's whisker was one of the earliest diodes or detectors. That was pretty much made out of galena. In 1909, there was a physicist named William Eccles that discovered the crystal diode oscillator. In 1926, Julius Edgar Linfield, another physicist, proposed and patented the field effect transistor. So that was in 1926. He wasn't able to build it, he wasn't able to demonstrate it, but he had the concept and patented of the FET in 1926. From my schooling, and I think most of yours, 1947 at Bell Labs was Shockley, Bardeen, and Bertan that demonstrated the first point contact transistor, and that was the first transistor made. And then in a couple of years later, 1949, Motorola started a research and development laboratory in Phoenix, Arizona to research solid state technology. So I think it's kind of very advanced for them that the first time a transistor was ever created, that they jumped in and started to analyze semiconductor technology. So since they're a Chicago company, so why would they go to Phoenix? Well, again, Dan Noble was well known for his work in FM, and he was one of their leading scientists. And back then, it was difficult to find anyone that knew anything about semiconductors. And they hired, researchers, PhDs, et cetera. And a lot of them didn't want to go to Chicago. It's just too freaking cold. So they said, let's go to Phoenix where it's not as cold. And then I think this is an interesting turning point. So 47, Bell Labs demonstrated or created the transistor. 52, just a few years later, in April, they had a symposium where over 100 representatives from 40 companies paid $25,000 each to license a patent to make transistors technologies. And that created they were able to not only license the ability to make transistors, they were also able to attend a 9-day transistor technology symposium, which included a visit to Western Electric's transistor manufacturing plant in Allentown, Pennsylvania. So one could say that there's Silicon Valley, but really Silicon Valley wasn't the beginning of silicon. It was Allentown, Pennsylvania in 1952. And there's this interesting footnote that there were participants from such electronic titans as GE and RCA, as well as from small firms like Texas Instruments and Sony. There was also a note I found that in 1952, Motorola licensed transistor technology from Bell Labs. So they started looking at transistors in 49, or semiconductors. And then in 52, they said, well, let's license it. I could not find a connection that said they actually attended this symposium, but it's so close that it's, coincidental, and they probably did. And Motorola realized they had all these products, these, radios, AM, FM products, consumers, TVs that could benefit from solid state. The early applications were power supplies, amplifier output stages, automotive alternators. And just 10 years later, Motorola Semiconductor had 4,000 components on the market. So let's jump into kind of what their product line looks at. And I'm going to, this came from their master selection guide in 1978. The logic family, they had CMOS, emitter coupled logic, transistor logic, DTL, RTL, etc. And notice that, you know, most people think of the 7400 series as the TTL standard. They had others before that, which I can only think were, they're driving customers back then were mainframe computers. You know, there was a lot of people that, get cut off my notes, you know, got control data and Burroughs and RCA and Xerox that a lot of them used ECL, a lot of them used TTL. And so I counted all these up, and there's about 15 different versions of this logic. So you can imagine keeping a company busy, building the same thing over and over and over, you know, AND gates, OR gates, NAND gates, flip-flop, shift registers, adders, whatever, 15 times in all these different families. And just for interesting, I kind of dug out a little history on this, and if you look at resistor transistor logic, that was basically, you always have a final gain output stage, and then you have, here's like a NOR gate, you got an A and a B input, and a summing junction, and that was RTL. Of course, you can kind of guess the issue with this is that if A is high and B is low, you've created a voltage divider. So this could kind of pretty much end up in the middle of the threshold, and the noise immunity might not be that good for RTL, but that's all they had. The next stage was DTL, diode transistor logic. So they had diodes, which provided more isolation. You could pull them high and low, and it would, you know, eliminate the current flow in one direction, and that was better. But then TTL, they would put an active transistor in the input, and that worked like DTL, but you actually had gain. So you had some gain, which means faster switching, and that's much better. Then back in the 60s, the most blinding thing in the world was ECL, emitter coupled logic, where you basically had these transistors. Here are the inputs A, B, and C, and you just grounded the emitters, and you tied them high for the output. And this was the most fastest thing there was in the world. It burnt power like crazy. But in 1962, Motorola introduced the Motorola ECL, or MECL as they called it, which was the really first monolithic integrated circuit. So they made ICs out of ECL before RTL or DTL. 66 was MECL 2, 68 was MECL 3, that had the 1 nanosecond gate propagation time, worked at 300 megahertz flip-flop rates. In 71, they had the 10,000 series, which is low power, and then the 1981. And like I say, this was heavily driven by the mainframe people, you know, with like control data, Burroughs, RCA, Xerox, it's mini computers, whatever. Then there was the CMOS. The obviously CMOS is low power. This is a field effect transistor. The metal oxide field effect transistor, or MOSFET, provided, it worked like a vacuum tube. It had a very high impedance. It created a very nice, you know, low power mode. It started out with NMOS, where you had the drain here and the load up here. There was the PMOS, where you had the active part up here and the drain in the bottom. And then finally, you went to CMOS, which was both N and P to be complementary. And this kind of provided a both pull up and a pull down. Up here in the NMOS, if it were off, you'd have a power. If it was on, you'd shut it down. So this was the best of both worlds, and it finally took the world to get to this because it was, consumed large areas of die. And of course, CMOS is the way the world is today. Linear interface. So op amps, voltage regulators, bus interfaces, peripherals, numeric drivers of displays, telephony products. Just to give you an idea of some of the linear interface devices, again, driven by the mainframe technology, a tape drive, 9-track tape drive. Here'd be the tape. You had your read-write head. You had your electronic gain control, some filters, and a read-write amp. And you'd have this replicated 9 times for a 9-track tape. And then there were several support circuits to do that, like the cyclic redundancy check generator, error patterns, LRC, the longitudinally, I can't say it, redundancy check, polynomial generators, et cetera, skew, deskew registers. The heads weren't physically lined up perfectly, and they were out of a line, so the bits would come in at different rates or different speeds or different times, particularly if you wrote one tape on one drive and then you moved it to another. The mechanics of them would be slightly off, and you had to kind of skew and deskew the data. So that's another function of the linear family. Also, consumer. There's all sorts of linear consumer circuits for television, radio. You can see radio, the sound IF detectors, video, IF amplifiers, chroma keys, horizontal vertical processors, for games, the color TV demodulator modulator, radio functions, IF amplifiers, FM stereo decoders, complete AM systems on a chip, and then other weird things like an organ circuit, a 7-stage divider. So I guess this is like you start with a fundamental, and then you divide it down 7 stages for each of the individual other frequencies, and an attenuator, automotive, etc. So just I'm trying to give you just a broad, skipping a stone across the water of some of the things. This is just one of probably 50 pages of things that were this type of circuitry. Discrete, I'm not going to get into this a lot because you kind of know what power is and small signal and high frequency and regulators. Motorola made these for not only themselves for their own products, but they actually sold it to other companies. Optoelectronics, Mini Block. And then they started to vertically integrate. They made solar power systems. They made power supplies. They made liquid crystal displays, solid state relays. And so they were able to take their various semiconductor technologies and vertically integrate them. And to touch on a couple of those, of course, they were in Phoenix. Phoenix is pretty hot. It's got a lot of sun, a lot of opportunities for solar. And not only did they make the solar arrays, they made the mechanical structures to mount them. They made the voltage regulators to take the DC from the solar and charge lead acid batteries or lead cadmium batteries. And then liquid crystal displays. In the 70s, liquid crystal watches were the rage. They made the displays. And so there was about 30 of these products. I'm just showing you some of these. They had ladies' watches, men's watches, unisex watches, displays for small instruments, clock displays. And that was another thing that was, you wouldn't think of it as a semiconductor, But if you're processing thin films and lithography, it kind of fell into that bailiwick. Of course, memories, and just because they had, you know, ECL and TTL and whatever, they had a memory for everything. So they had RAMs, MOS RAMs, dynamic and static and CMOS. They had emitter couple logic RAMs to drive their emitter couple logic processors, TTL RAMs, electrically erasable. You might remember these. These things had a little window in it, and you could program them. And then if you didn't like what happened with the code, you could put it under ultraviolet erasable light, and under about 30 minutes, you erase it and you reprogram it. They also had programmable ROMs. These are one-time programmable, ECL, TTL, read-only memories, character generators. People would make display processors or teletypewriters, and they needed character generators for that. And also bubble memories. I don't know if y'all remember that, but that was kind of a short term, short life cycle thing. That the idea was you had a magnet in the top and bottom, and in the middle you had this substrate that had these little magnetic domains. And because it was magnetic, it was permanently information there. So if you lose power, you had the information stored in there. It was a giant shift register. This was like the original solid state disk. You know, SSDs are pretty common now. This was the precursor to that. And it just didn't really pan out, but it's something that people tried for a while. And then memory systems. Again, Motorola tried to vertically integrate. This is from a buddy of mine, Jeff Nutt, that Tom Starnes knows. And in 1981, since we were making 64K DRAMs, they decided, hey, let's make our own sister system. So they put a 2 megabyte board. This is a 2 megabyte board. It was 12 inches by 18 inches. It cost about $9 grand. And then they would sell you a chassis, and you could put 16 of them in there, and you could get a whopping 32 megabytes for about $150,000. And you can imagine that today you can get, you know, gigabytes on a little USB stick you stick in your pocket. But people were willing to pay that. You know, they made interfaces to mini computers like Data
Mike,
General.
what technology was that? Bubble memory, or what technology is this one?
This is 64K DRAMs. No, this is solid state.
Okay, all right.
Yeah.
I remember the promises when they first had bubble memory. They said that you could get a shoebox full of bubble memory, and it was so dense that it could record every song ever recorded in the world. You'd have
Cool.
your own portable jukebox of everything. Was it really that dense compared with today's silicon memory?
Probably not. I don't remember the densities. That's a good question. I forgot to. No, I doubt that. Of course, there were less songs back then. It didn't have to record as much. I forgot how big bubble memories were. That's a good question. We might need to Google that and try to find that out. I'll have to look up that later. But yeah, bubble memories, think of it like a solid state disk. You had to shift things in and out. It had some error issues, but it was, you know, magnetic, which meant it retained the power or information after it's powered off. So I don't know how dense it was for its time. Hang on a second. Let me just see if I can look that up.
So I guess today's FRAMs are relics of the original bubble memories.
Yeah, I don't even know what an FRAM is, to be honest with you.
The ferroelectric memory,
Oh,
non-volatiles.
Yeah, I think really, you know, anything magnetic, it tends to do high current, and it tends to take a lot of power, and I don't know that it really made it. I'm still looking. in a Wikipedia here.
I know Intel had a bubble memory operation, but like everything else, they got out of that pretty quickly too.
Yeah. Okay, here's something from Wikipedia that said a 1 centimeter square memory that stored 4096 bits was the same as the standard plane of core memory. So it looked like the main thing, being non-volatile, was its attraction. It was denser and faster than core, but didn't, surpassed by, semiconductor RAM. What is it? One application was Konami's Bubble System Arcade video game system, introduced in 1984. It featured interchangeable bubble memory cartridges on a 68,000 base board. That's interesting. The system required a warm-up time about 85 seconds. And anyway, it goes on and on. So I guess the thing wasn't the density, it was really the non-volatility. So there really has never been a non-volatile memory that has not been magnetic. And again, that means larger geometries and more power to push the magnetic domains around. But yeah, I think these are all 64K RAMs, and like 150K for that much memory was the way it was. But good point. I'm glad you asked that question.
Yeah, today we use flash memory, of course, or
Yeah.
ferromagnetic memory for dense non-volatiles.
Cool. So
I
you put all this
remember-
oh, go ahead.
I remember using those ultraviolet flash memories a long time ago, proms. That was amazing stuff.
I heard a story about a guy that worked for a company, and they had a bunch of these, and so they had their system. It was a rack, and it had microprocessors in it, and had a lot of these UV ROMs in it, and they didn't put stickers to block the light. And so a guy came in to take a picture of it for a brochure, and when he took the picture, it set off his flash, and the flash went into it and just drove the system crazy. It just got knocked it to its heels. So you need to cover those things up.
Yeah, the camera flash bulb flashed and zeroed out the memory, right?
I don't know if it zeroed it out or just kind of, flipped some bits momentarily, but it didn't like it. So all this stuff I talked about, there's packages. Okay. There was all sorts of packages. There were all sorts of speed ranges. There was all sorts of temp ranges. There was commercial 0 to 70 degrees C. There was industrial minus 40 to 85. There was military minus 55 to 125. And it'd be possible to take one die and put it into several packages over several temp ranges, over several speed ranges, and you'd have a dozen different parts. And Motorola Semiconductor in the 70s and 80s had over 25,000 unique products if you multiply that out. And so we were a broad line supplier. We were one of the few broad line suppliers back in its day. So the one thing I haven't talked about, and I really don't like this slide, I can't do it justice. We also had processors. We had a lot of processors and microcontrollers. And some of them we created, some of them we second sourced. And TI had a CMOS 141004 bit. And this thing was good for toys and games, and we second sourced it from some time for some reason. AMD had a 2900 bit slice, and a bit slice processor is you have a 4-bit ALU and you have another chip that's controller. And so you can cascade these things. You can have one controller and four 4-bit ALUs and make a 16-bit processor. And a lot of mini computers use this as the heart of their system. They were really micro-coded, had writable control store, and they used the 2900. And then we took it and made the same thing in ECL for just blinding speed, emitter coupled logic. Of course, the 6800, the first microprocessor, the 6809, which was the heart of the color computer, the Radio Shack color computer, it had a good life. The 6801 was a microprocessor, which meant it had the CPU, peripherals, timers, memories, all on one chip. And that branched out into multiple follow-ons. The 6805 was the lower end. It became CMOS, which is valuable. And again, it had its own family. And then not all people know it, but we also made Intel 8051s. And this is just like a second source. It was an internal customer. They wanted a backup for the 8051s. Even though we didn't sell it on the open market, Motorola made Intel 8051s. Then, of course, the 68,000, and Tom Starnes was the, one of the marketing managers for that. He can tell you all about that. And one thing I haven't included was, all the follow-ons, the 68,010, the 20, the 30, all of the peripherals. There's like dozens of peripherals. The 88,000 RISC, the Power PC, the Apple, IBM, Motorola consortium. And then what I worked on was the digital signal processor, the DSP 56000, which is a 24-bit, which became the de facto standard in the audio industry. There was a 16-bit version and a 96-bit floating point version. I also worked on a vector engine, the VComp 701, which never saw the light of day. It was an internal, lab project that we tried. It didn't work didn't make it to the market. And then there was a thing called LonWorks, the Neuron, and this was for industrial control. And this, I think it's still around. It's called Echelon. Echelon's the company. So we made the original ones, and that was supposed to go into industrial, light switches and motor controls and that sort of stuff, and network together. And then I had this little thing up here at the top, the 14500. We had a 1-bit processor, and this seems to intrigue everyone. So I'm going to spend a little time on the 14500 1-bit processor. So this is the block diagram. You come in, your data comes in, it goes into a LU, a logical unit, not an arithmetic logic unit, because it didn't do math. And an on-chip oscillator had 4 bits for instruction, and then the output. Here's the die. Here is a demo board, development board, and here's the entire instruction set, having 4 bits for the instruction. It had 16 instructions. 2 of them were no-ops. It had a no-op for 0 and a no-op for an F for highs. And it was pretty clever that the reason was they figured that if you just go into Never Never Land and you just go run out of memory and you're executing just the state of the bus with no memory, if it's 0 or 1, then you can pulse a flag and reset the thing. But it had load complement, and complement, or on complement, etc. And that was the whole dang thing. And the idea was to replace relay logic. So, my dad did this stuff. My dad did relay logic, where you have your power line and you have these contactors or switches or sense switches or push buttons. There's A, normally open, B normally closed, C normally open, D normally closed, and then you had your load. And this is exactly how you would code it up to where you'd like load in A and then complement B and in C and end in the complement of D, and then store that out to the load. And this was the logic equivalent of that. Now, being a 1-bit processor, you know, it didn't do a lot. It needed a lot of support circuitry. And here is a block diagram of a 14500B chip. Well, first of all, it doesn't have an on-chip program counter. So you had to have an external program counter that you'd click off, and it would go into a memory. And it was typically an 8-bit memory. And 4 of the bits would come out, and that would be an instruction path. And then you had another 4 bits that would go out to some muxes that one would be a 8-to-1 input selection. The other would be a 1-to-8 output selection. And it would bring this information in and out of the 1-bit data line. And it did require a significant amount of support circuitry, but the idea was that this chip in 1977 cost $7. The typical microprocessor cost $70, and so it was 10 times cheaper. And still, the typical microprocessor required external memory and peripherals and all that. But these are all cheap CMOS chips. So you could probably have for like $25 a functional system to do relay logic replacement for like traffic lights and you know, presses and you know, things like that, versus, you know, a couple of $100 for an 8-bit processor. And there were a lot of guys out there, like my dad. They understood relay logic. They didn't understand these newfangled microprocessors. So this had a short kind of a window. And in the back, for everything I've talked about, there are links. And so there's a link to this data sheet. There's a link. They had a wonderful applications manual. It's over 100 pages that shows you how to build these systems to replace relay logic. Now, what's odd about this is in 1977, you would think that this thing had its glory days of maybe 5 years and then died. Well, there are people today that are still buying these things. You can get them on eBay for like $4. I don't know where they're getting them from. And they do just wackadoodle stuff with it. And here's this guy that has decided, I want to make one out of vacuum tubes. So here is 14500 1-bit processor vacuum tube version. I don't know why a rabbit's there, but here's his data flow. And he's been tinkering around on this thing. I've been touching bases with him. And then, like most engineers that just can't let good enough alone, he says, well, you know, it'd be better if it had this. It'd be better if it had that. So now what he's done is taken the vacuum tube 1-bit processor and expanded it to 12 bits. So he's trying to do math with this thing. So if you Google MC14500, you're going to find it's like a cult. You're going to find all sorts of guys out there doodling around with this thing. But I just think it's funny that today it's got a life of its own. Okay, I started Motorola 87 or 78, I'm sorry, as an application engineer in South Texas, Louisiana. I represented all the parts you saw before, all 25,000 parts, but not every single one was used in the area, so it was a subset of that. And here are some of the interesting customers I stumbled across over the years. Our area was not really a large manufacturing area, so people went through distributors. Our distributors are Hallmark, Hamilton Abnet, Schweber, Sterling. A company in New Orleans, it's still there today, it's called Peller and Milner, and they make giant washing drying machines. This thing is about 8 to 10 feet tall, and it's got multiple sections. Pardon me. And so this is for if you need to wash sheets and bed sheets for a cruise ship, for a hotel, you know, hundreds or thousands of bed sheets a day. These are giant industrial washing machines that were relay controlled. that we converted to microprocessors. I called on NASA. They didn't use a lot of semiconductors. They were mostly IBM mainframes and Interdata, but they had interface logic, and they bought a little bit of dibs and dabs of this stuff. And it was just fun to go visit. And they were nice enough one day, they let me fly the space shuttle simulator. So I jumped in the cockpit, took a spin around the Earth, and I crashed it. But at least I got to go to NASA, fly the simulator. That was kind of fun. There was a company in Freeport called Intermedics. They made pacemakers. And so that was all CMOS circuitry. Motorola had a policy back then, we would not be designed into any life-threatening technologies. And so they had to get their CMOS from other people, but they required support circuitry, and they would have controllers that they could interrogate. So if a person had a pacemaker in their body, they could put a inductive coil on their chest and talk to it and interrogate it and find, the battery life, the lead corrosion, things like that. And we sold like 6809s into their interrogation controllers and programmers. National Instruments, that's another big startup. Motorola had the first IEEE 488 general purpose interface bus chip. And that was their goal, is to make instrumentation. So myself and another salesman, Casey Brown, we delivered one of the first IEEE 488 GPI-B chips out to the fledgling National Instruments on bee caves and handed it to Dr. Trouchard, who started that company. IBM was in Austin, we called on them. Texas Instruments was in Austin. I talked about us making liquid crystal displays. Turns out TI made liquid crystal watches, but Motorola made the displays. We made the CMOS chip for the timer inside. We made the crystal, that was another division, but we made the crystal to time it. And basically TI took our 3 chips, or i3 products, crammed them into a case and had a battery, and that was it. And that was their TI watch. Company still alive in Austin, Ola Research. They have devices, instrumentation to test ballistics. If you have a gun and you want to know how fast the bullet's going, they have this little thing you can set up and fire through it, and it will give you the speed of your shell. Data Point in San Antonio, they were the first company to create a local area network, the ArcNet. They were also the first company to create the microprocessor. They created the 8008. They built a TTL version of a processor architecture, and they reached out to Intel and TI and said, hey, here's our architecture. The first guy to make it wins. You have the rights to it. TI said yes. Intel said yes. TI said no. So they took their TTL version, put it on a chip, and that was the 8008. So that's just some of the applications that I was, worked with when in the late 70s, early 80s. I went into digital signal processing. I wrote the DSP training course. There's a cassette version, and there's a 4D instructor-led version of 800 slides. I'm still looking for this. I'm sorry I gave it away. So if any of you have the MTT31 800-page instructor-led DSP training course, please reach out to me. I'd love to copy it. And DSP, went into cellular, the audio industry. We had a 96-bit floating point version. I talked about the VComp 701, which never made it to production, but it created the largest patent the patent office ever saw, with 450 citations. Another thing I worked on was video communications. This was a video codec and a 24-bit DSP. This is for the audio. This is for the video compression. We actually got this thing working. We were working in conjunction with British Telecom, and we got it working over ISDN, which is 8.320, H.232, which is the internet, and the plain old telephone system, H.324. We were working with Sony on one of these, and so we had a prototype box. Sony had a prototype box, and I talked to one of the guys, and let's take it home and try it. Let's just plug it into the internet, see what happens. This is before quality of service, QoS, and the dang thing worked. But one thing that we learned about that, you know, people who do video conferencing today didn't know about it was, this is my customer, and it was in his bedroom, and there was a mirror behind him, a mirrored wall. And not only could see him, I could see his backside, and he was sitting there in his underwear. So here's my customer in his whitey tighties. I had to kind of ignore that and pretend I didn't see it, but that was that.
Mike, it sounds like the original Dilbert.
Yeah, pretty much. I mean, it was a funny moment that it's kind of like, hey, how you doing? Can you hear me? Hey, can you hear me? Can you see me? And I could see him, and I could see he's, you know, he's sitting there, and he had a white shirt and a tie on. He just took his pants off, you know, and that was the weird thing. And the last thing I worked on was 2008 4G LTE. This was Motorola Semiconductor was way ahead of themselves in 4G. We had an amazing RF group, so we created this breadboard, and the intention was to make a chip, but we just had a breadboard. We sent it to the World Mobile Congress in Barcelona. We were the only people. We were the first people there, and we were we showed video, we showed audio, and everything was great. And we won the Diamond Chip Award, which is the highest award Motorola can provide in semiconductors, me over there. And then that was a year later, that was kind of the end of my career. So that's kind of thing of how things winded down. And then what happened to SPS? Well, in 1999, we split off on Semiconductor, which was popcorn, power, analog, whatever. 2006, Freescale split off. 2015, it was absorbed by NXP. There's rumors that NXP might be bought by Samsung, but we don't know anything about that. But that's pretty much my presentation, and I thank you for your time. So that's the end. I'm going to take about a 2-minute bio break, and you guys talk among yourselves, and we can continue on from there. So thank you for your time. I'll be back.
Yeah, thank you, Mike. So you guys have any question, open up your unmute, and also turn on video you like, or you have some story to tell. Go ahead, or raise your hand. So Dennis, I saw your name pops up.
Yes. So I kind of spent the first half of my career doing hard electronic design, worked for many years for a company called Accelerators Incorporated. I am almost certain that I spoke to Mike Collins in his early years. Mm-hmm. I was first a field engineer in 1973, part of 74, and then started designing electronics. So I designed in a lot of Motorola parts and a lot of TTL stuff in the early days. I wanted to go to microprocessors, but we frankly couldn't afford it. And then eventually I did do some microprocessor work. I'm pretty sure 6805. And I had other people doing programming. It's not my line, but I do circuit design and flow diagrams. A lot of nostalgia there for me.
Yes. Yeah, Bob, that's the best selling product, 6805 for a lot of applications.
I'm back. I'm kind of catching up on things.
So Tom, probably
So-
you know which microprocessor do we sell the most? Is it 8-bit or 16-bit?
Which one did we we
the
sell the most?
Yeah,
Boy, I don't,
or quantity or volume.
yeah, I mean, I was in the high end microprocessor stuff.
Yeah.
Um,
So you got Apple,
you know, so we had Apple,
Yeah. then PowerPC
yeah.
and other stuff.
well, I was a marketing guy basically, and let's see, we got the 68,000 and a whole bunch of video games. And that was a lot of fun because I went to Chicago a lot because there was a bunch of the pinball guys and stuff up there. I barely made it through college due to the attraction of pinball, and video games started as well then. But it was fun going to those kind of places because you get to see what, what the next designs were about and everything. We sold the chips into a lot of printers, though AMD later got a hold of a lot of that business from us using their 29,000s. I don't know, I'd have to sit down and think about all the applications that we had.
68,000s went into a lot of Unix workstations.
Oh, they were
early on.
absolutely on the workstations. Yeah, that was a huge, basically made that industry. Yeah, I went to Boston a heck of a lot because, with the guys that started out doing the word processing back when you had a word processor, and they were up in Boston, went to Cambridge and
Data General.
Wang worked.
Wang.
Yeah.
Wang's the one I was thinking of. Yeah.
Okay. Yeah.
And so if you ask how many, by the way, you always have to say, well, how much money turn into revenue? Because you can sell a lot of little 6805s going into little simple things, or you can sell some of the more powerful processors and memory chips and stuff, and make a lot more money. And in the end, it's not necessarily how many you make, as how much money you make, and then do you actually make money on it? Or as we used to say, sometimes you wrap a dollar bill around each one you send out, which maybe you're just sort of buying into the market.
Yeah.
There's a few questions that I didn't see because I was talking that popped up and I'd like to address. One was the first process was a 4004, and that's correct. And maybe I am in error that Data Point had the architecture 8008. It might have been the 4004, but anyway, I do know that Data Point used their a terminal. They started making glass teletypes in the late 60s, and that's what Intel based it on. So it might have been a 4004. Other thing, NI was prolific in the IEEE 48 GPIB, but didn't it originate from AP and the HPIB? Yes. HP created the instrumentation bus, they created the HPIB, they created the architecture, they did all that, but Motorola was the first company to make a chip, the MC68488, that did the HPIB function. And, that made it economical enough to put NI into business. So thank you for bringing that up. And that's the whole point of this. I mean, my God, I'm 70 years old, and this is from 50 years ago, and I like this discussion and keep me honest. So
Yeah. I was in Hong Kong for a few years, from 89 to 92. The PC market was taking off, and these drivers are all in Singapore. So we keep the XC11 and DRAM and SRAM, and we can support all these driver manufacturers. So that's one good product that we sold in the PC market, X11.
Yeah. Also, the 1605s, the CMOS, they went into, Motorola kicked themselves in the butt for decades for losing the PC to the Intel, and yet, they said, but they kind of were licking their wounds and saying, yeah, we lost that, but look at this. I mean, we're in the mouse, we're in the keyboard, we're in the disk drive, we're in the disk controller, we're in the serial processor. And so there was, they got the CPU, but we got half a dozen different peripherals.
Yeah.
IBM was really trying to cheap out using just an 8-bit data bus, and we were so proud of our 16-bit one, and so Intel won the deal at IBM out of that little tiny group down in Boca Raton, and nobody expected that thing to go anywhere.
Yeah,
we're still cussing it.
Does anybody know any computers that were built from the Intel 4004, which I believe was the first processor?
I don't think so, and I wonder whether it was the first or just the first one that Intel made, because as Mike mentioned, I worked at TI, though that was much later. So maybe it's hard to know. But we had TI had a small 4-bit microcontroller that went into. There were little games that there was a football game. It seems like, was it Hasbro and
Speak and Spell?
Yeah, the first computer I'm aware of, and I certainly am not as old as some of you, is the IMSI 8080, which had paddle switches. And I first noticed that as a kid. You had a cassette to store the program, right, and you programmed it on the front panel with binary. I'm not sure what you did useful with it, so they hadn't yet discovered how to sell it to people.
No.
Like just having a computer that you can program and, have lights blink.
Well, the first thing was definitely the hobbyist. It was the S100 bus. That was definitely Intel. And I think it was the 8008. I don't think it was the 4004, or maybe it was the 8080. I don't know. But yeah, and I don't know that Motorola, I mean, back then it was the Wild West. People would cobble together all sorts of stuff. So maybe there was a 6800 on the S100, but I don't think so. It was primarily an Intel world, and also maybe Zilog. I know Zilog got in there big too.
I believe the 4004 is considered more of a controller, not a computer. I have one device that has a 4004, and it was a medical device that the nurse would carry around and take temperatures and store other, medical things, and it would come back to a base unit that had the 4004 in it, and it would print out the patient's data.
Yeah, so you're probably right on it not yet being a computer, because the IMSI used the 8080, which came after the 8008. And I believe that the issue with the 8008 was needing negative power supply. I think you needed, I think they went
2 or 3 power supplies. Yeah.
Yeah, there was the -12 and plus and -5.
And again, that was one of the beauties of the 68,000. It was a single power supply.
Yeah.
So the 8080 was the third one, I believe, and eliminated some of the power supply issues.
Yeah.
And then the IMSI 8080, which is easy to web search, I think was like the first I'm aware of. I mean, maybe someone has come up with something for a general purpose computer, but that would be like at first in my awareness. And I'm seeing 75, December 75 for the release date.
Yeah. Well, and just not just MSI, but I think they were based on the S100 bus, and there were several S100s, and then there was what the operating system was CPM. I think CPM was the first operating system for that, and then they had some apps, and that was, they had BASIC, and I think they had a spreadsheet programs, and people were actually running their companies off of that stuff back then, before the PC really kicked off.
Yeah.
I wanted to tell you a couple more stories. I was talking about data point, and no, I was talking about Intermetrics in Freeport that did the pacemakers. And one was when I was visiting them, like I say, Motorola would not let anybody put any of their chips into something that was health critical, goes into a body, whatever. So I think they used the RCA, they had a CMOS Cosmac, and that was the processor that went into the pacemaker. But you had to talk to it and interrogate it. And so I went into a guy's office, and he had this little box, and it had a little CRT screen on it, and it had a way to select the different pacemakers to program them. So they had, like, pacemaker A, pacemaker B, pacemaker C, I forget the name of them, but then they had one pacemaker that was in development and hadn't been released, and it was called, the code name was Lazarus. So they had a pacemaker called Lazarus, which is biblically bringing you back from the dead. And the other thing I remember about Intermetrics was that they were going to go to a trade show. And if you remember back in the 80s, some of you, there was a commercial from Sears about the Sears Die Hard battery. Like, we took these 5 cars and packed them into a Minnesota snowbank, and in the morning only one started, had Sears Die Hard. Well, they did something similar, and they had these 5 guys that were in a wool coat and a hat and all that, and they said, we packed these 5 men in a Minnesota snowbank overnight, and in the morning only one started, and it's at Intermetrics, and there's one guy jumping up and down smiling, there's other 4 just kind of keeled over backwards into the snowbank. And while it was a funny marketing gig, their management didn't like it, and they ripped them all up and said, we got to have those, and don't get those out. So, but that's some of the funny things I stumbled across.
That was before YouTube.
Yeah, just a little thing. The Altair 8800 was before the IMSI, and it's considered the first PC. And it also brought out the S100 bus. So that was the bus designed for the Altair 8800. And then the IMSI was a clone of the Altair. And it was released in January 75. So everything happened very quickly. And they just copied that bus. And it's recognized as the first commercially successful PC, also because it had Microsoft's founding product, Altair Basic. So I guess they were still in the closet at Gates dropped out of school, and I guess he was at his parents' closet making that.
He's still CPM and made it MS-DOS.
Yeah, so they didn't yet have that DOS thing, which it came out later. So I'm guessing it had a unique operating thing, kind of like BIOS. And then, but he did have Altair Basic, which was Microsoft's founding product. So, and of course, everyone's forgot that because, once he headed into that meeting for the PC with IBM, no one remembers anything before that. It's like he was born on that day. And but actually, he was beating on lots of things. I'll send a link out on that Altair thing.
Didn't didn't IBM create the operating system and they didn't know what to do with it or didn't care about it? They said, we're a hardware company, and Gates says, I'll buy it from you. I think he bought whatever, an early version of MS-DOS. I think he got it from IBM, and he just
Yeah.
took it from there.
There was a guy in town in Seattle that had the operating system, and Microsoft bought it for a song and then sold it to IBM. IBM wanted his BASIC, right? That's what he was selling and developed.
So
But-
IBM had the
they
hardware.
IBM wanted his BASIC, and they said, well, do you have an operating system? And he didn't, but he said, sure. And he got somebody else. The guy got enough money that he wasn't unhappy about it, but should have asked for some shares.
That's not the complete story. He misled the other person about what he was going to do with it.
Yeah.
And
No doubt.
then so the other one got enough money after some big lawsuits. So
Good.
so basically Gates was a schemer, or like he saw what basically to make something useful to saleable, you needed something to run on it, and they saw, I guess, his basic thing from the Altair, and then they still needed the operating system to boot up. And it's kind of funny that IBM couldn't just like hire employees to do it, like why they even bothered talking to him. But he said, I have it, and then went to someone else and minimized the value of what the thing would do, what CPM modified would do, and then sold it to IBM in Florida. And then, of course, once everything blew up, then you can probably web search the lawsuits and see, when the other one finally figured it out that the CPM had been turned into something like the PC, the IBM PC. And, but anyway, it all sorted itself out, and, they all retired happy.
Maybe IBM had higher integrity, and they knew there was something out there. They just wanted to hire somebody else to copy it, and then they could say, "Hey, we don't know where this came from. The guy said it was legit."
Yeah, basically, IBM were compartmentalized, and the group that built the hardware were happy to get anything from anywhere. So rather than trying to deal with some other part of the company, if someone would just hand it to them and they write a check, that was basically, they'd be out the door and in market. They wanted to be selling something. So the fact that he could turn it on short time, with low effort on their part, that was the whole attraction. And because everything was going so quick in the industry, it was really accelerating. I mean, when you look at like the first one was the Altair in like January of 75, and then they were already being cloned by the IMSI in December. So it took less than a year for another company to basically copy and be selling, something and try and make some money. And so everything started getting quicker and quicker. And IBM, the biggest thing is how slow they are. And I'm sure they had a hardware group. They had the stuff. All we need is the OS and the BASIC or something, so you can get some useful software. And he's standing there and saying, well, I can do it in a few weeks. Basically he scrambled and was apparently in the closet with I think Paul Allen, and they worked day and night without sleep. So that whole model appealed to IBM, and they didn't really care, as long as they had it and were selling. And they sold it in 82, right? It was I think late in 82. And
that was 74, 75, 76. That was like a inflection point where things just vectored off for the entire microprocessor world, because there was them and us and Zilog and TI had a processor, and RCA had a processor, and National had a processor, and they had a 16-bit. We were all, just scrambling for each other. There's probably three I forgot, but
And Apple came out with the Apple II about 78, and as I remember it, IBM was actually behind, And so all they cared about was time and being out the door with, you know, something cute. And even then it wasn't as good as the Apple. You know, Apple was still more refined. And I remember my parents bought it at that time. And the reason that drove them to spend the money, the whole thing cost them $8,000, but it was the business software. So you could buy the Apple thing, but it was kind of, it's like the same issue which persisted, that you could get drawing software in that, but all the main business things for real business were still on the you know, you were driven to the PC. So they managed to corral offices, like real business offices, and then the Apple thing, you could doodle and you know, make pretty things. You know, which is how the whole industry sorted itself. If you were a graphic person, you wanted an Apple, and if you were, you know, had a company, you needed the counting on the PC.
But I remember, Morris, that the first project management application, Microsoft Project Management, came out on the Apple long before. It was on the Mac long before IBM offered that on their IBM devices. So I had to actually learn Microsoft Project, even though all of our office was full of IBM equipment. We had to go to the University of Utah and learn it on Macintoshes in order to use that application.
Oh yeah, yeah. I mean, this is before when you had everything on every device. You know, like I can remember that too. That actually even using both, right? Because like PC board layout still had to be on a PC. Like, I mean, there was something on an Apple, but it just didn't work out right. You know, so that, but they were feeling left behind. So IBM, by the point they were getting out the door with that, were way too slow, and the market literally was escaping them. So, you know, it was all just that Gates was real smooth, and instantly when they wanted something, he had it. You know, things that he didn't really have, but you know, he realized where he could get.
It's all about, it's time to market, and Tom and I know this, and we hate it, is that Motorola had amazing architectures, amazing architects, amazing engineers, and to design the more complicated systems, it took time. And Intel would always come out early with something that is subpar, but get the design in, you know, and we'd always be a little late with a better solution, but they just, that's the way it worked, you know.
Yeah.
I want to share something. Can I share one? I have a couple more slides to share if I can.
Yeah, you can do a share screen, yes. I think you can
this has nothing to do with what I was talking about, but again, I will send out the presentation. Here's all the links to everything, even to the vacuum tube 1-bit processor. But I just love this slide. This is the internet in March of 1977. And that's all it was. And if you look around here, you can kind of read some of this, like here's MIT, and they had PDP-10s.
I'm not seeing anything, are you guys?
Oh, you're not? Okay, well, all right, hang on a minute.
Yeah, close it and then reshare it. Close the other, reshare it. Got it. Wow.
All right.
Very complicated.
Now, complicated, but it's maybe 200. Complicated compared to today, there's billions of people on the internet, but this was it. So there's MIT, WPAFB, some Air Force base, Illinois, Utah. You can read all these things. Harvard. This squiggly line is satellite links to Hawaii. And the way to get on this, and here's Texas. I was at Rice at the time, and we were hoping to get on, and we didn't. But this is what it took. It took this monster honker box, this rack called the IMP, the Interface Message Processor. You had to have one of these puppies to get on the internet. And here's the physical thing, December of 1977, that showed them clustered. And can you imagine where we are today with this stuff? that's the beginning of the internet. And now you got it in your hand on your phone, and like in my house, I got I probably got 15 devices with phones and TVs and computers and all that stuff. So I'm sending this out in the presentation. I just love this slide.
Okay.
I heard down in the lower right was NSA. I wonder if that's the
Yep,
real NSA.
they're there. ARPANET, MITRE, yep.
Yeah.
Yeah, I'm wondering, I've been since the 70s in the downhole petroleum drilling business where high temperatures are a big concern. And
Yeah.
CMOS brought in parts that we could use. CMOS lost some interest for a while there in the early 80s, but then CMOS came back. And really when we got to the 68 CO32, that was a really panacea for us. We could actually get some 16-bit and 32-bit processors that would do
Really?
a lot of stuff and work at high temperature for us. So that was really beneficial. And I know that most of the work on SOI and CMOS wasn't directed for high temperature. It was directed for rad hard, and yet the same design layout characteristics and methods that make things rad hard also happen to make them work reliably at high temperature. Did you see that as well?
Who are you addressing? I don't know.
To Mike or Tom, I don't know if your DSP work was intentionally trying to get more rad hard capabilities or high temperature capabilities, but they came along for us.
Well, first of all, I feel you because, like I said, I grew up in Tulsa, Oklahoma, and worked for Amoco Research Lab. And then I moved to Houston, and I worked for a company that made instrumentation. And I spent a year at Willex, so I know about downhole. And the point is, Motorola over designs. We don't intentionally, go for a specific market, but here are our temp ranges. So we had commercial, industrial, military. So minus 55 was plus 25 was the most we would design to and guard band and test to. And if you got beyond that, then, good luck to you. You just got the luck of the Irish. So yeah, it just, we always over designed. There was bigger guard bands than that. And yeah, I know there was a lot hotter temperatures downhole, but yeah.
Well, but all of these things you're showing here, Mike, basically it's the same damn chip, and it's a matter of where on the wafer that the chip was, how good that run was, and you just tested it out. You tested for the most extreme case. Okay, all you guys that didn't make it to the extreme case, then you go to a lower temperature.
Yeah, you're commercial.
And all that sort of stuff. There were so many things because there's power consumption. There was, like you say, the speed, what kind of guard band you got going on, all that sort of stuff, and what the customers want, and therefore how much can you charge for it? You charge out the wazoo if it's rad hardened. The rad hardened you had to go through to do it in ECHL or something like that, which was a reasonable redesign. And those were completely different chips, let's say, but there were people who would buy the military grade CMOS stuff, and some outside company would then super test all that, or what they call the life test the stuff, and the stuff that survived after 168 hours and all that sort of stuff.
Yeah, that's what we had to do. We would buy the MIL 883C qualified versions of all of the highest grade industrial and the military available parts. And then we'd have to test them beyond that because we have some designs that need 200C operation.
Yeah. And you probably had a shaker table and all that. If you get, I don't know, 1 out of 10 works, then you're happy. I don't know.
Mike or Tom, did either of you work with Jerry Healy at Motorola or Freescale?
So ring a bell. Jerry Healy? No, I don't.
Gary Healy, yeah. He was one who worked with me back in the 80s, and then he quit the oil field, got his PhD, and went to work in processors for Motorola.
Cool.
Don't know him.
And also, you know, if we design something for -55 to 125, it doesn't mean it's going to fail, particularly if you kind of widen up things. Like if you want to widen up the voltage, the rails, you know, instead of being plus or minus 5%, you're going to go plus or minus 10% and give it some more, you know, power, or tighten it up, or you know, we call it PVT, pressure, voltage, temperature. You know, we do it over those metrics, and we had to kind of pump things out the door by the millions to make money. And I know you're looking for kind of like the extreme corner cases that we didn't really serve that market, but if you got a handful and it worked, then that's kind of good for you. And then how do you solder those things down? I mean, 200C, doesn't that kind of like melt the solder, or what?
You have to use high temperature solder,
Okay,
almost
yeah.
pure lead, high lead solder.
Okay. Yeah, I worked a year at WellX. I worked on their cameras. I was I had a slide in my previous, I worked on their fiber optic CRT in 76. Well, cool. Kai, it looks like it's about, what, 30 people online? And
yes, about 35 earlier. So now it's down to 19.
Okay. Well, is there anyone else that would like to chime in? These are great stories. This is what I wanted to hear. You know, I didn't want to dominate it. And anyone else want to jump in and say hi or tell you what it's did? I'd love to hear about you.
Yeah.
This is Bernie Pappard. I worked in the high-end microprocessor group, mainly on the 68,000 stuff.
What's your name?
And Gary Daniels made the comment that the 68020 was an opportunity of a lifetime. But it turns out, I think the HC11 was really the opportunity of a lifetime. When the part came out, it had all kind of production yield problems. And as Tom Starnes said, you'd ship parts with $1 wrapped around them. I think Gary Daniels said $5 were wrapped around the parts. Anyway, Gary Daniels was a great design manager, and he assembled a task force of, I think, 30 engineers, and there was no silver bullet. There was a whole bunch of yield problems. And eventually, you know, they sold, somebody that worked on the HC11 would probably know more about this than me, but I think they sold more than 1 million parts. So it was probably the highest volume part that Motorola ever made. And well, like I said, Gary Daniels, I thought was a great design manager, used a lot of common sense and got the results that were needed.
So you probably remember his stories about he'd give a motivational lecture and it'd have to be tied to some sort of Civil War battle.
Right, always some military thing.
Yeah. Yeah, just I said before, I think all the disk drive manufacturers are using that XE11. So we always running short in Singapore. So actually, we have a credit manager station in Singapore to collect money. We sell them probably want to make sure we get the money.
I think even AMD licensed the whole chip and puts it on some of their chips, maybe even today. I don't know the whole story on that. So it's been licensed even to other semiconductor manufacturers because at this point it's pretty small.
Well, one of the topics I guess I haven't really gone through is the how the economics drove the industry. So basically things where they needed really high temperature were just ignored because you didn't have massive volume, or RF where I worked, they could dominate the world with a few days of manufacturing. You know, they didn't use enough silicon to keep the factory going. So the design effort or focus in life ends up being very narrow on what uses the most dye, you know, or generates the most, but maybe not the human benefit. In other words, like, you know, your things that you really need in life, like your oil drilling or your RF, great RF parts to make a better phone, no one really cares about. But if you can suck up the silicon, then everyone's all over it. You know, 0 to 70, and it goes in a car and does some logic function. You know, so I think they got a little bit on the lazy side and rode the probably the automotive controller thing even far more than things like PowerPC or dominating where Intel was, when they could have done better, just because of, you know, how much silicon you can eat up and ignoring oil and everything. Anyway, other people probably have other comments like that.
Well,
That is Motorola. Yes, that's in our name. Automotive drove us. Also, you know, the RF and all that stuff and consumer, we were driven because we had parallel vertical companies. TI, AMD, Intel didn't make radios and TVs and walkie-talkies and two-way systems.
So actually try to serve Motorola Inc. before. So Motorola was the biggest customer making equipment, two-way radios and cell phones and all those stuff, consumer product.
They actually bought outside the company, and it wasn't really the real focus was what uses silicon, and that ended up being a very narrow product focus, and you'd get knocked out of the production line even, you know, for things like microcontrollers for vehicles.
Yeah,
but it made the company progressively less diverse. So, you know, where you look in the 70s and they made, you know, anything soup to nuts. And if there was a new thing, they wanted to do it, including things that were labor intensive, like hybrids. So they were the dominant world supplier of cable television and broadband hybrids, so low distortion modules. But you had to like have a human or, you know, wiring it up. So you had dye on there and then someone to solder little transformers, right? And so they owned a market, but I don't think in the end they really cared, because you could knock out those microcontrollers for cars, right? And it was just easier money. And so that leads you to kind of lose your sharpness, you know, so you're not into RF, you're not into downhole drilling, you know, all the stuff that makes it interesting.
Unfortunately, I don't think anybody's online that worked on the HC11, but I think the beauty of it, they designed it for some camera manufacturer in Japanese. I don't even think they realized the myriad of applications it would end up in. So it ended up, because it was a microcontroller, it ended up, you know, broadly used, a lot of different applications.
I use the HC11. One of the companies that went into the Baker Hughes oil field company was Develco in Sunnyvale and Santa Clara, and later on Mountain View. But Develco made a lot of products that were digital downhole tools that relied on the HC11, and it was pretty prolific. I mean, prolific in our business is building and selling 200 of these per customer per year. So for a total fleet of 20,000 maybe over a 5-year period, that was high volume.
Yeah.
I'll never forget our trip to GM. We had a research group from the oil field that went up to GM's headquarters in Flint, Michigan, and looked at their research things. And we talked about what things we could do to improve our ability in high temperature, because of course, on engine inside the high temperature compartment was now a new focus for automotive when they started applying SOI and things there. And we said, we have a problem getting some of these parts. We just, we're only going to use maybe 20,000 of these in the industry this year. And they said, 20,000 part? They said, we would not even ever decide to make a part or buy a part if it was only good on the Corvette, and we make 250,000 of those every year.
Yeah.
So our volume has never in the oil field justified any product development in semiconductors.
Yeah.
So who has ever heard of Motorola Seguin?
Or CB radio, yes.
If you, well, more than that, if you drive, they're not there anymore.
Yeah.
But if you drive south on I-35 and about New Braunfels or so, or actually San Marcos, take a left and you drive out, and then all of a sudden, boom, there's this flat plain, there's nothing, and then this big hunker factory pops up, and it's Motorola Seguin, and they would assemble things. They made CB radios. They made a lot of the Ford engine controllers. When microwaves are new, they made the front panels to about every single microwave there was. They made car radios for Ford and Chevrolet. And it was just amazing that what Motorola Seguin did. They weren't part of SPS, but they were our customers.
Yeah. Well, I think the only other smaller microcontroller companies, microchip.
Microchip technology.
They sell a lot of 4-bit, 8-bit stuff, 50 cents. Maybe it's not lower now.
Well, they actually have done a pretty good job of whipping what's left of Motorola's MCU business as well, though.
Yeah.
You know, I think 2 days ago maybe their stock kind of cratered, but
Oh, really? Yeah. Well, they were General Instrument before in Long Island.
Yeah,
That's my first job, Long Island.
Oh,
I
yeah.
make a pacemaker in a 76 time frame. So to kill a lot of dogs.
yeah. Yeah, Steve saying he bought that, or
Yeah.
he
We
took
make
it over.
for Medtronics.
Yeah.
They're still doing that. They still actually the big dog in the field, Medtronics. So now it's getting late. I would like to thank Mike and all the people who speed up and talk about the experience, sharing the experience, and from different fields. I really appreciate that. So I'm going to request Mike to send me the slide. I'm going to post it in our website, and this was recorded. It's being recorded. I'm going to post it in the YouTube. So I'm going to send that out later on in case you want to review what's going on. But I wish you all a good night. So see you next month.
Thank you all for being
29.
great.
Thank you.
y'all for
Thank
being
you very
great
much,
audience.
Mike.
Mike.
Yeah.
Yes,
Thank
Mike.
you.
Thanks, Mike.
Yeah. Okay. Bye-bye.